My final year project is on demand forecasting by incorporating sales patterns of product groups. Accurate demand forecasting is crucial for industries with both high lead time in production and high inventory costs for holding stock. If demand is incorrectly estimated, it can have negative consequences for the retailer's cost and revenue. Therefore, our goal is to use clustering methods with the aim to improve weaker performing predictors and therefore improving the overall forecast accuracy, while our secondary goal is to generate potential insights on the product groupings created by clustering. We start off with pre-processing the raw data into time series for pipelines, normalizing and scaling the data if necessary. We then introduce a novel approach by extracting features from the existing data and incorporating sales data across different products via clustering on the extracted data. We evaluate their performance in improving weak predictors using XGBoost to perform the forecasting. Deeper insights on the data, like feature ranking and analysis, can also be retrieved using factor loading analysis. As NTU has partnered with Beckton and Dickinson, there are two datasets used in this research, the BD's internal product demand dataset, as well as the publicly available M4 dataset. The paper will focus more on the M4 dataset and evaluate the model's performance on the M4 dataset. Leveraging the use of manual and automatic feature extraction algorithms, we are able to extract more than 700 relevant different features from each time series after filtering, which allows us to apply different clustering algorithms. The more prominent features are listed in this table below, such as the Forer entropy, kurtosis, partial autocorrelation, skewness, as well as variation coefficient. In order to understand which features are significant, we perform feature ranking by using factor loading analysis. Factor loading analysis is a powerful tool for exploring the underlying structure of complex clusters using principal component analysis and the eigenvalues generated. By ranking the features by their absolute factor loading values, we can identify the features that are significant in each cluster and relevant to the product in each cluster. For the M4 dataset, there are about 160 significant features found. After extracting the features, we apply a clustering method on top of these features, using 4 different clustering methods. These methods include k-means clustering, as well as dynamic time warping, which is useful for comparing time series that may have different lengths or non-uniform time intervals, as it allows for alignment of the series by stretching or compressing the time axis as needed. The Liew method is a fast and efficient algorithm for clustering and community detection networks. It is a heuristic approach that aims to optimize a modularity measure, which quantifies the strength of the division of a network into clusters or communities. Lastly, we also have deep embedded clustering, DEC, which is an autoencoder based method for unsupervised clustering, which means that it is used to group data points into clusters by optimizing the KL divergence between soft cluster assignment and an auxiliary distribution. Our results from table 3 show that the baseline metrics for non-cluster models were relatively consistent with each other, while the bottom table shows that the performance of XGBoost is significantly improved by applying clustering methods to combine different time series to train the same model. Deep embedded clustering achieved the best performance among the clustering models. Although DEC outperforms the rest of the models, the computational time required to run DEC is way more significant than other models, and therefore there is a cost-performance trade-off for extremely large datasets. Using the red line as a benchmark, we can see that the clustering model significantly improves the results as the predictor is weaker, while being a detrimental effect to the strong predictors. In the full pipeline, the strong and good predictors are segregated out to different pipelines to ensure that the strong accuracy is not compromised by the clustering method. Since our novel approach would be more beneficial to the weaker performing time series, it is important to separate the dataset into 2 to retain the top performing predictors using the non-clustering algorithms, while improving the weaker ones using our novel approach. Utilizing the feature extraction method, we are able to provide an approach that is able to offer better accuracy while enabling analysts to gain more insights into the dataset as well as product groupings. And this concludes the video summary of the project. Thank you.